welcome everybody. So to our next installment of the CSE Fall Colloquium, where we're bringing to you research talks from groups across the department. So today, the UW Reality Lab gets to own the Colloquium. So what is the Reality Lab? We just launched this year in January with a focus on doing research and teaching in augmented and virtual reality. We have a web page, we exist. Basically the goals of the lab are to create the technologies to power the future of AR and VR, to do the things that are beyond what the companies are doing for maybe the shorter term bottom lines, to do the longer range research for this, and to educate the future researchers who are going to be faculty basically doing research and teaching AR and VR, as well as developers who are going to go out into industry to a lot of these companies, and creators for making sort of artistic products that will fit into AR and VR. So we're currently funded by Facebook, Google, and Huawei. So this is an industry-funded effort. It makes a lot of sense to do this in Seattle. We're kind of, I hate to use this word, the epicenter of AR and VR. Facebook has Oculus, but Oculus Research, now Facebook Reality Labs, coincidentally, we got there first with the name, by the way, is in Redmond. Google has a major presence in AR and VR in Seattle. Huawei has a research group in Bellevue with doing a lot of work in the kind of AR, VR space for mobile in particular. But also Microsoft HoloLens was done here. Valve Vive was done here in the Seattle area. Magic Leap has a big presence here. Anyway, this is really a great place to be doing this kind of research. So the leadership of the lab is myself, Professor Ira Kemmelmacher, and Professor Steve Seitz. So we're the co-directors of this lab. We also have our core members. Barbara Moens she's been leading the effort for animation production for years, and now she is the director of the Reality Studio, bringing that kind of storytelling into VR. And it's a great challenge, and she's producing already exciting films in this space. And our director of research and education is our very own Aditya Sankar, who may or may not be here. Anyway, so Aditya is leading particularly a lot of the efforts for undergrad education and research. And our program manager is David Kessler, who is also the general manager so he kind of keeps everything working for the lab, and he's also the general manager for the Ig Nobels, which is kind of, anyway, you should check that out if you haven't already. It's kind of sort of Nobels for interesting research that is kind of off the beaten track, often very humorous. We also have an advisory board from all of the companies, really luminaries in the fields of computer graphics, vision, virtual reality. We're doing a lot of research. We're rolling out courses. A capstone that Aditya is teaching right now is ongoing. Barbara's Reality Studio, creating films in virtual reality. We have a lecture series. You're probably getting a lot of emails about that, but we've been bringing in really world-class thinkers, researchers, visionaries to come teach us all about what's going on in AR, in VR, and what the future looks like. And finally, an incubator for undergrads to kind of go beyond a class and develop ideas that could be, can be prototyped and put out in the wild, released through Steam and so on. So finally, getting to the research, we actually are funding research with a bunch of groups, not just our own group. So we had a call for proposals, and 20 proposals came into the lab for research, and we've managed to fund 15 of them. 14 different faculty are currently funded. Their students are currently funded to do research for the Reality Lab. And the board basically helped us to make those decisions. So today you're going to see 6 different projects from a variety of different groups. Some of them were kind of foundational projects that basically raised our profile and helped establish the Reality Lab and got the sponsors excited about what we were doing. And some of them are stuff that was just funded in March, basically, is when we launched the funding process. And you'll get to hear kind of the latest, greatest from a bunch of CSE postdocs and students, and one EE student as well. That EE student is up right now.
Hello everyone, my name is Elyas Bayati. I'm a PhD student from ECE department and Archival Management Lab. Today, we propose to design the next generation of visors, which can open a new window to optical advancements in this field. Near-eye visors are one of the most vital components of head-mounted displays, as you can see, and people for designing these near-eye visors use freeform optics and waveguide-based optics. However, as you can see, these structures are bulky, complex, heavy, and even their field of view is limited when we place them close to eye. And this came from this fact that people rely on geometric reflections and refraction problem. So to bend the light and close to eyes. So what we want to do is we want to make these AR visors smaller, lighter, and if you want to make them close to eye, we still want to have large field of view, like in ordinary glasses. So we've developed a new type of visors, which combination of reflective visors and waveguide-based visors, which use the nano-scatterers. So these nano-scatterers are cylinders, as you can see, which in the dimension of 100 times thinner than human hair. So we can change their diameter, thickness, and even their periodicity in a square lattice. Their material is silicon, which is like glass. We can see through them, and they are transparent. And we can change their diameter so we can get the different phase and amplitude response. So using this technique, we can convert any optical freeform shape or any phase distribution to the group of nano-scatterers, as you can see, in like a flat surface. We call these flat surfaces Metasurfaces. As you can see, they are really small, and we can fabricate them. So usually we fabricate them in a smaller size. Recently, we could fabricate them in large area and larger scale. As you can see, their size is comparable with our hands, so we can fabricate them for AR glasses or even for ordinary glasses. So last year, we developed first metasurface-based visors. Using metasurface, we could navigate light from display to eye with a large bending angle. So these features help us to get larger field of view. So the field of view that we could get is comparable with HoloLens 1 or Magic Leap 1 with like current famous AR visors. So we could get around 77 degrees by simulations. We designed these visors by numerical simulations and ray optic simulations. This is the phase value or phase max that we could get with these visors. And using the same technology, we can convert them to the group of nano-scatterers. So the problem that we get with these visors is the see-through quality. Because we use just one single metasurface, the see-through quality that we get is not that good. So currently, people use another prism to solve the see-through quality problem. We want to be able to view the environment as we would with the regular protective goggles. So this requires imaging rays comes from infinity to our eye without any distortion and low optical power loss. We kind of use a similar idea to solve the see-through quality problem. We use another metasurface to correct any distortion caused by first metasurface. So when I say metasurface, I mean group of nano-scatterers that I mentioned before. So we proposed this stack of metasurface to solve this problem. And for designing the phase of the second metasurface, we use the same idea, numerical simulation and ray optic simulation and optimization to get the better see-through quality. As you can see here, this is the phase of second metasurface. For comparison, we do the simulations for wavefront error. So we use wavefront error because we can see how much our imaging ray is different from ideal case, which is here is a parallel case, as you can see. The RMS that we could get for metasurface visor is around 3 times of the current visors, which is not that bad, but we are currently working on it. And ideal imaging rays system is around a quarter of lambda, which is, we are trying to get it better. But currently we are working to optimizing this phase. However, what all we have done is a single color. So one of the longest standing problem which diffractive optic of metasurface has is chromatic aberration problem, so which is famous with rainbow effect. It means that optics behave differently for different colors. So here I bring an example for you. We use metasurface lens to do the imaging for this image. As you can see, we got different focus for different colors. We have the same problem with AR visors using metasurface. As you can see, we design AR visors for green light, and the visors bend light differently for red and blue. So fortunately, there are some solutions for that in metasurface field. One of them is dispersion engineering. It means that we can change the diameter of these nanoscatterers in a way to get the kind of similar phase profile or desired phase profile for different colors, red, green, and blue. So we want to use this idea as a future work for our AR visors. So if we use this dispersion engineering, we can bend light in a similar fashion for 3 different wavelengths. However, this is not our ideal case. We want to do the full color operation and broadband. So because for this, if we use the dispersion engineering, our display should work just for 3 discrete wavelengths. So recently, our group demonstrated the first full color imaging using Metasurface and combination of that with computational imaging. The idea was this. Instead of using a lens to focus in a single plane, we use type of Metasurface lens which focus along optical axis. So, and we do that for 3 different colors and find the same overlap for different colors and do the computational imaging and reconstruction with the convolution. So as you can see, the result is kind of better, and we kind of solved the aberration problem for Metasurface. We're going to use the same idea for AR visors in the future, and this is our future work. That concludes my talk, and I would be happy if I answer any question. The time was limited, so thanks.
All right. Hi, everyone. I'm Edward, and I'm going to talk to you about the work that we presented at SIGGRAPH Asia almost 2 years ago, and it's called Emptying, Refurnishing, and Relighting Indoor Spaces. And the idea with this work, I'm just going to set up like a theoretical example. So let's say you wanted to rent an apartment. So usually what you do is you would go visit it, and it would probably be filled with its current tenant's furniture. But the point of you visiting isn't to see what the current tenant's bed looks like. It's you want to be there to imagine what it'd be like for you to live there. So you have your desk in the corner, your Mona Lisa on the wall, your shelf in the corner. You might want to say, okay, if I change the decor, how would it look? Or you're visiting in the morning, but it's got a west-facing window. How would it look in the evening? So more concretely, what we want to do is say take an image or several images of a scene, so this image over here, and then be able to make modifications to it for the purpose of visualizing what it'd be like for you to physically actually, move this bed out and put in your couch over there. So how do we do this? So your first thought might be, okay, I've heard of this tool called Photoshop. It's got this great content-aware fill stuff, and I can download some images of furniture from Google, and so that's what this poor misguided real estate agent did. This is pulled from some like BuzzFeed list of 20 worst real estate photos. Anyway, so you can tell they're. So what happened here was this is like an empty house, and they decided, oh, we want to make it look more attractive, so we're going to Photoshop stuff in, and it doesn't look realistic at all. So in contrast, we want really visual realism in the scene edits. And so like the reason is, it's pretty obvious. The whole point of this kind of application is for aesthetic evaluation of, what it would be like for you to live there. And so if we want to think about what is it that makes, this Photoshop unrealistic compared with, good scene editing. And to answer that question, we have to think about, for realism, it's really about as I said before, if you actually physically made the changes to the room, what would it look like? And so that kind of points to, how do we physically see things? So brief overview, you're going to have a light emitter, because we're talking about light rays. So the light emitter, it has some color, some intensity. It's going to shoot out some light rays. Those light rays are going to bounce off of an object. They might get scattered by other objects. And finally, those light rays will hit your eye. So with that very brief description, we can kind of identify 4 elements that are important for the physical reason why you perceive things. So the first one is the light emitter properties itself. So where does the light come from? What directions is it going? How bright is it? What colors? There's the 3D geometry. So where do these light rays bounce off of surfaces? Where are the surfaces? One really important one is the materials. What are the surface scattering properties of the surfaces that they hit? So, when a photon hits an object, it'll, get absorbed and then probably re-emitted, maybe at a different wavelength in some particular direction. And then finally, there's the properties of the viewer. Where is the viewer? What light rays do they perceive to make up the images that we're going to be producing? How sensitive are they to particular wavelengths, and so on? So with these 4 elements in mind, I can talk a little bit about how this works. So the first thing that happens is that we take an RGBD scan of the room. So this is a Google Tango sensor. And then from that, we perform a bit of processing to get this whole 3D model of the room. So this has the 3D geometry of the entire room and also the appearance of the room in high dynamic range. And this is really important because, in a single camera image, if you took a picture of, outside the window, either the window would be blown out or, the area under your desk would be completely dark and you couldn't see anything. So you really need this high dynamic range. From this model, then we can do some simple geometric processing to get semantic scene geometry. So what does the empty room look like? Where are the walls, floor, ceiling? Where is the window? And where are the doors? And then finally, we also care about the materials, as I mentioned before, and the light emitters. So I won't go into too much detail about how we did this, but I will focus on the fact that the realistic light modeling is maybe the most important part of this work, and in particular, it differentiates it from a lot of the previous image manipulation types of works in the literature. So traditional graphics lighting models are these simple idealized models like, perfect, rectangular area emitters or spotlights or point lights. But if you think about real light sources, they're a lot more varied and complicated, particularly in their angular distribution, as you can see in this large set of examples over here. In our work, we set out to be able to model these in realistic ways such that they could represent accurately the appearance of light sources that we see in real-world scenes. So for example, we can model point lights that have varying directional distribution. So in this example, on the left is one of the original input images, on the right is our reconstructed empty room version of the scene, and you can see that this standing light shoots most of its light upwards but a little bit downwards, and we've managed to capture that as well in this image. Similarly with line lights, like the fluorescent tube lights, like these lights up here, they're lines, they're not just points, but similarly they also have directional distributions. So again, a lot of lights throw most of their light upwards. In fact, if you look at the lights in this room, they do that, and the room is actually lit by the reflection of that light off of the ceiling. And then finally, you also have things like windows and area lights. In order to do all this modeling, we're not actually taking a camera, sticking it on top of the light and measuring how much light there is coming off there. We're actually looking at all of the indirect reflections that are going around in the scene, it's basically a large nonlinear optimization problem to figure out the distributions and the properties of these light sources. So I'm just going to show you a few more results now. So these are original input images from 4 different scenes. And now from the same camera angle, empty room version. I'll just flip back and forth one more time. So it's obviously not exactly the same, but it captures most of the feel of being in that room. And you can stick in whatever furniture or spheres or graphics models. You can do other things than just modifying the geometry, of course. You can change the materials. You can change where the light sources are and their properties because we have the full 3D model of the room. I'll just show you one more example of one of these fade-in, fade-out sequences. And I think these really highlight the strength of our method in the aesthetic sense. Despite all of these changes that you're making to the room, it really feels like you're sitting in the same room. And then finally, just to say something about the camera angle thing, since we're constructing a full 3D model, we're not constrained to the original input images. So you could do something like visualize this in AR, so walk around this emptied room in an augmented reality sense, or a refurnished version of it. Thanks.
Hi, I'm Jungjun Park. And I'm excited to present our project, Surface Lightfield Fusion. It was recently published at 3DV 2018. It was worked with Richard Newcomb and Steve Seitz. So we present the Surface Lightfield Fusion that can produce photorealistic appearance reconstruction from a handheld commodity RGBD sensor. In this video, the synthetic rendering accurately models the high-quality textures, specular highlights, and even interreflections and shadows that induced by global illumination effects. Our system takes input as RGBD and IR video streams and outputs an appearance model of the scene. Our goal is realistic reconstruction of target scenes, and besides from sharp textures and nice specular highlights, we try to achieve global illumination effects. which is such as the interreflections, where the white paper appears reddish because of the object, and the soft and sharp shadows highlighted with green circles. Although these global effects are critical to the perceptual realism, modeling them has traditionally been very difficult. Our key idea is that unlike traditional BRDF methods that enable scene relighting, we can trade off the relighting for the ability to capture diffuse global illumination effects. And we achieve this by posing the appearance reconstruction as surface light field estimation problem. Prior works on appearance modeling can be split into two categories. One is parametric BRDF estimation, and the other one is non-parametric image-based methods, each of them with pros and cons. The model-based methods involves modeling the complex global light transport, and because inverting the global lighting is extremely difficult, most previous works simply ignore these effects. On the other side of the spectrum, image-based representation naturally incorporates the global effects, but it requires dense view sampling on the hemisphere, which is unsuitable for casual scanning. In contrast, surface light field fusion is located in the middle of the spectrum, combining the benefits of both model-based and image-based methods. Specifically, we achieve this by considering the factorization of the surface light field into view-independent and wavelength-independent components. And we model the components with image-based and model-based respectively. Please refer to our paper published at 3DV for further details. The resulting system reconstructs the surface light field without the dense view sampling while capturing the global effects. We note that, however, because we do not recover the full BRDF, our captured models cannot be rendered under new lighting. We now go over the implementation of our theory. Our system gets RGBD input stream and reconstruct the geometry using Kinect Fusion. And the high-resolution texture is then fused in real time. Next, our system segments the scene into regions with similar materials. And for each material segment, surface specularities are measured in IR channel. Finally, with captured environment lighting, a realistic novel view of the scene can be synthetically generated. To estimate the material properties of the scene, our systems start with segmenting the scene into regions with shared reflectance properties using deep convolutional neural networks. And material segmentation is necessary because it is infeasible to recover BRDF for every single surface point. Given material segmentation and estimated camera pose, we use the IR projector and camera attached to the depth camera. And given the light source model and IR intensity images, we optimize for BRDF parameters. The estimation works robustly in practice for a wide variety of surfaces. For example, for a brushed metal surface in the image, the right image shows the IR image, and we can see the specular highlight from the projector. The specular highlight in the IR image is vertically elongated due to anisotropy. And we can fit a reflectance model from the IR signal, and our fitting is quite close to the ground truth. And same for the wooden surface in the bottom row, where we can accurately model the specular highlights. And rendering the recovered material clearly shows the vertically elongated specular highlights that characterizes the appearance of brushed metals. Our final scene is one with multiple objects. Our surface light field renderings of the scene is virtually indistinguishable from the ground truth. Notice how our system captures the rich global light transport effects, including the soft shadows and occlusions, which cannot be modeled with other pure BRDF-based methods. So we introduced the first casual surface light field fusion reconstruction framework. Our system effectively captures global illumination effects and specular highlights. And we show that by factoring the surface light field into view-independent and wavelength-independent components, we arrive at a representation that can be robustly estimated with an RGBD camera and achieves high-quality results across a wide variety of scenes. Thank you very much, and that's it.
Hello, I'm Junha Roh, and I'm working with Andre Pronobis and Ali Fardi and Dieter Fox. So the title of the project is TwoPlayer Game for Real-Time Natural Human-Robot Communication. So what we are trying to do is to train a robot which follows a human speech direction, like go straight, turn left, and the car should follow that direction. So in order to achieve this, we would like to set up two-player game of driving, which requires collaborative manipulation and navigation through two players. And we thought the virtual reality is a good environment for natural interaction to extract some information. So this is a demo video of actual game. So we asked two people to play driving game, while the one person will do the operator, who can see the view and drive the car in the VR, while the other person do the commander. So he can see the whole view of the operator's view, and also the entire map and the specific target. So he can send some command to operator, and the operator will react to that speech signal. So from this game, we would like to collect some control signal and the speech signal. And before moving on to the real game, we build a simple environment with a maze. So this is 2D maze simulation, and the input was simulated 1D laser sensor. And the output is the velocity, linear and angular velocity. And we refine the dimension, like command, complexity of the command to three types, two types, turn left and turn right. So we analyze the structure of the maze and randomly start the agent, and we test it on the maze environment and also on the real scan data of CSC building. So we find our agent navigate well. So we build a new city environment for longer driving sequences, and also we had a gaming wheel and the pedal for a realistic experience. So in the middle of the screen, you can see the actual instance of driving game. I don't think you can listen to the actual voice, but currently one of people saying like some commands. And I manually annotate these into straight, left, right cases for labeling. And this is current result trained on this environment. So it's a little bit noisy, but it follows some directions as we change some labels. So you can see some labels in the upper left side of the video. So currently we are working on language input. So instead of using the direct speech signal, we transcribe this speech signal into sentences, and we give a stream of words like turn left and some pauses, and we transform our network to sequence model to react properly. So thank you.
Hey, hello everyone. I'm Chong Yiwen, a PhD student in Grad and Reality Lab. I'm excited to be here to present my research work called Photo Wake Up 3D Character Animation from a Single Photo. The work was done by co-working with Professor Brian Cullis and Iraq Milmacher. So let's start. Okay, so this is Stephen Curry. People know that. And yeah, actually, the image captured the moment when Stephen Curry made an important three-point shot. And time was frozen when the image was captured. And our goal is we want to wake up the photo to bring the Stephen Curry to life again by animating his body. So here's the result. So quite fun. And actually, our technique can be applied to a large variety of photos. So this is a Banksy graffiti we download from internet, and this is our result. Okay, so another case, Wukong. People know that, a cartoon character in comics Dragon Ball. And this is an image, and this is our result. Okay, so the last one is one of my favorite. This is Picasso painting, and we can date that. So check out this. This is our result. Okay, so this is one of my favorite. And okay, so because behind the technology, we actually rebuilt a 3D human model of that character. So if we have some augmented reality device like HoloLens, we can in some way bring the character into real 3D world. So I demonstrate in this video. So here I virtually hang up the painting on the wall of the building and bring it to the real 3D world. So actually, to rephrase the goal, in order to wake up the photo, our goal is, given that photo, we hope we can rebuild a 3D model of that human character. And also, we want to make it animatable because it is important in our scenario. So the high-level idea is that we leverage the movable body model, which is trained by lots of real body scans and allow user to control the shape and the pose with parameters, which is good in our scenario. But unfortunately, a movable body model is naked. So to tackle the problem, we propose a two-step to solve the problem. First, we fit the body model based on body pose to get approximate body model. Then we warp the body mesh to match the body silhouette. And hopefully, we hope after warping, we still keep reasonable mesh geometry and skinning weight, which will be used for animation. So here we go through our pipeline in a very high-level concept. Given a single image, this is our input. We detect 2D pose and segment the human mask. Then based on 2D pose, we regress the parameter of movable body model to get approximate body mesh. Then we extract the skinny mat and the depth mat from the body mesh. And depth map represent the mesh geometry, and skinny map represent the animation information, which tell us how to move the vertex on the mesh when the pose was changed. Then we warp the both maps to match the segmented human mask to get a new maps. Then we rebuild our mesh, the front part of our mesh, by combining these two maps. And also we repeat the same process to rebuild the back part of our mesh by virtually rendering the back view of the body model. Then finally, we rebuild the texture, and we implant the occluded part of the background image and put the mesh on the background, then apply the motion sequence in our database, like running, to finish the wake-up illusion. So here, we want to see more results. So LeBron James, Messi, and unknown girls. So this is a movie poster. And Beatles. And still Banksy graffiti. And we can take you back to the time, back to the moon, have a moonwalk. The same, Wukong. And Iron Man. Oh, sorry. another painting. And we can also do something like this. Last one result is about augmented reality result. We can see some of the result. This was a download video from HoloLens. This is Beatles Albert Help. And this is Picasso painting. Here we demonstrate we start the motion, then look around the mesh, and later we will make it run again. This is a CSU building. I think people know that. Okay, so that's all. Thank you.
Hello everyone, I'm Costa Ramatas and I'm a postdoc at Grail and UW Reality Lab. And today I will talk about our project Watching Soccer in Augmented Reality. And this project is together with Ira, Brian and Steve. So the goal of this, the idea behind this project is to take the experience of watching a soccer game live in a stadium and bring it in our living room. And we propose to do it with augmented reality. So now we want to take the whole experience of the game and put it in our space. And so the game is represented as a hologram where we can watch it with an augmented reality device such as HoloLens or Magic Leap or any of these. And traditionally, the way of capturing sports is done by going in a stadium, and then you can put cameras around, then you have to synchronize them because you need some frame accuracy for the reconstruction. And you feed all this data from all these cameras to a cluster where you estimate the volumetric representation of the game. However, this is very expensive, and it's also very difficult to have a setup like this or getting data from other companies that did something similar. And then we thought that can we just do it from a single video? How we can achieve a holographic representation of a soccer game, but by just logging a single video. And in fact, this is what we did, is that we have an input, a YouTube video, a single YouTube video, and this is the actual hologram of the game that we see through a HoloLens. And back to our approach. Our goal is to have a video conversion to 3D. So, as I said before, our input is just a single YouTube video. And on the right, you can see the reconstruction that we have from that video. We want to have a learning-based approach since we have a limited amount of input. And so for a learning-based approach, we need data. And we found out that it's very difficult to acquire real data, but it's very easy to have data from video games. So we had to play, and if you pass through Grail and you see us playing, it's for science, so it's not for fun. And yeah, essentially the game gives us texture and the depth buffer. So it means that for every player we know how it looks like, but also what is the depth of this particular player. And we can use it for as a 3D shape representation. Essentially, we have pairs of images and players' images and the depth. And knowing the camera parameters, we can convert the depth maps into meshes. So we have about 12,000 of those pairs. So the first thing that comes to your mind is, of course, training a deep neural network. And we did that. We used a stacked hourglass module that takes as an input the RGB image and the mask of the player and outputs its depth. So the depth is represented as an offset with respect to a plane that is passing through the middle of the player, which pretty much says that the darker, the darker the pixels, the further away from the camera, and the brighter, closer to the pixel is closer to the camera. Now, since we have a method for estimating a 3D shape for the player, we have to go back to the YouTube videos and have a big pipeline of actually finding out which pixels correspond to every player. So we start with an input frame. And we estimate the camera parameters. For that, we take advantage of the known dimensions of the soccer field. We perform player detection and pose estimation, and also we track the players. Additionally, we have an instance segmentation for separating the players from the background, but also from each other. And then we are able to use our network for estimating the depth for every player and for every frame. So now we have a 3D mesh for our video, from our YouTube video. And we take also the pixels that they come directly from the video, and we apply it as textures. And here are some results. So on the bottom right, you can see the original input video from YouTube, and it's the actual reconstruction of from our system. Luckily, it was accepted as CVPR. Otherwise, we will have to re-render with different banners in the background. Okay. So, this paper appeared on CVPR this year, and we have also code and network models on GitHub, so you can try it and for your favorite team. So yeah, now I would like to talk a little bit about work in progress and what we have been working right now. So here you can see our reconstruction is pretty nice, but something is missing. So where is the ball? And this is actually a difficult problem, because in the beginning we were thinking that, okay, just track the ball. And again, so if we apply like a state-of-the-art ball detector, we will have something like this. So the ball sometimes is occluded, sometimes we miss detections. So it's not very accurate, and we cannot really rely on detection systems. But even if we say that I will go and I will manually annotate every frame where is the ball, essentially I have something like this, which doesn't tell us much about where is the ball, because unlike the players, for the players we make the assumption they are always on the ground, but for the ball we cannot make the same assumption, because you have shorts, you have long shorts, so it's part of the action, and it's important to model also when the ball is in the air. So the main problem is that you have this ambiguity. So for example, these two trajectories, the red and the blue trajectories, they are different in 3D, but once you project it in the image, they have the same 2D trajectory. So there is an ambiguity over there. However, we can use physics for estimating a more reliable trajectory in 3D. So pretty much what we want to do is that we want to find the points that we know their 3D location, for example, when the ball is on the ground or when it is being kicked. And then we can connect these 2 points by just using physics. So we can use projectile or linear motion for connect points for short or long shorts. And how we can estimate this critical point? So if you have some trajectory like this, you may think that we can just use simple heuristics for finding where the velocity change and try to fit parabola in between them. And this is true when the data is very clean, but when it's you have noise observations, then this thing doesn't apply anymore. So we experimented and we found that it wasn't very reliable for having such heuristics for that one. However, we found out that we are able to use image trajectory. So pretty much we generate an image of how the trajectory will look over time. So you imagine of it as a long exposure of the ball trajectory. And we can use color to incorporate time. And then we formulated it as a localization problem. So we want to know where a force is being applied in a particular trajectory. And we train a network for this. And the training data came from a game engine, so we used the physics engine from Unity, and we had a setup like a box where the ball is being applied random forces. So we're having all the necessary 2D and 3D information and forces for training such a system. And actually, then we managed to get something like this. So now we're able to have the ball. And of course, there are some smaller problems that it needs to be addressed. For example, I can play again, and you will see that for the second bounce, the player is far away from the ball. But this is something that you can use the pose information for associating the critical points with the correct place in space. And finally, another aspect of our original system is that it was very slow. So now we're working on having a real-time version of this system. So we hope that we will achieve real-time performance by just scaling to many cores and many GPUs. And this can be done fairly easily by just writing by using Scanner, which is a program from Stanford, and enables to generate the computational graph of your program and run it in multiple machines and cores. So yeah, this is from my side, and yeah, thank you.
So I guess that kind of wraps up. Were there any questions about any of the projects? Kind of saved it for the end. I tell you what. Oh yeah, go ahead.
I wanted to ask about Chongyi's work. When he has the Picasso image going out of the picture, how is the background reconstructed?
Just enhance the background. I mean, patch bands method to use the picture to enhance the background.
Well, I think you can we'll keep the speakers around for a few more minutes so you can come and ask them more questions. But for now, let's thank them for all their work.